So let us start. At this lecture, we consider the problem of equilibrium and stability of open thermodynamic systems. So, equilibrium and stability of open thermodynamic systems. So, what is the problem and what we are going to study at this lecture? Let me recall that a closed system in thermodynamics is a system that do not interact with environment. An open system is a system that interacts with environment. In fact, we know that all the systems that exist in nature do interact with environment with up to lesser or bigger extent. This means that the concept of closed system is in fact an idealization, while all the real systems are open systems. That's why we can address ourselves two questions concerning the equilibrium state of open system. And we have two interconnected, let's say, issues and two subjects we should consider. The first one is how to find equilibrium state. This question is not trivial because the second law of thermodynamics applies only to closed system. And we know that in closed system entropy tends to its maximal value. In open system, we should have some similar condition, but what is the condition we have to find? The second problem is slightly different. We know that open system interacts with environment. This means that there are uncontrollable fluctuations in parameters of environment and in parameters of the system. And this fluctuation should not break equilibrium state. This means if any fluctuation happens, the system should return to initial state after some time. So the other question is, what is the stability condition for equilibrium state? The stability conditions are very important in thermodynamics because they ensure that an open system can stay in its equilibrium state for infinitely long time. And we are going to respond to these questions at the lecture. I suggest to start from a very simple problem setting. We consider the first question and we consider very limited problem setting. Let us imagine that we have our system, our thermodynamic system. And it has two thermodynamic degrees of freedom. That means that the extensive parameters of the system are internal energy, entropy, and some other parameter which I will denote by V. I will say that V is volume, but in fact this is just simplification. In fact, instead of V, it can be any other parameter. Let's say the amount of substance, for example, or maybe length, or maybe something else. And this is our system. And we have an environment. We will characterize the state of environment by the same parameters, internal energy, and internal energy of environment I will denote by UR, entropy S sub R, and volume V sub R. And this is a system. As far as the system is open, it can interact with environment. And it can exchange. There could be exchange of energy. And volume. In any process that happen in environment, this happen. Okay. And what we see, the system that includes the system under consideration, an environment, is closed. This means that the total energy which is the sum of energy of system and environment is constant. The total volume is also constant. And these quantities should not change in any processes that happen in our closed system. As for the energy, the total entropy is the sum of entropy of system and entropy of environment. This system can be changed in processes, but we know that it should go to its maximum value. This means that with some time the total entropy of the system will reach in its maximal possible value, and then it will not change. So, when the total entropy is maximum, we have an equilibrium state. For this big system, that includes our subsystem and the environment. The law of transitivity of equilibrium state tells us that if we divide the system and let's say disconnect the system and environment for some time, and then bring to contact again, nothing will change. This means that the total entropy, the condition of maximum of total entropy, determines the equilibrium state not only for the whole system, but for our subsystem too. And to study the first question, we should to consider necessary conditions of extremum for the function, for this function, total entropy. And we can consider two different approaches which give one and the same result. I will start from very simple consideration. Let us assume that some amount of heat, which I denote delta Q, came from environment to our system. And let me say that okay, delta Q, and let me say that some work is done, okay, delta Q, is done by the system on the environment. Okay, let us find the change of total entropy. Let us assume for simplicity that the process is quasi-statical. So let us apply the first law of thermodynamics to the system and to the environment. Let us first apply the first law of thermodynamics to the environment. We have, let me recall, the process is quasi-statical. dr dsr minus pr, P is the pressure of environment, dvr. From here I express the differential of entropy. One over T R dur plus PR divided by TR dvr. This comes from the environment. Now I apply to the system. I get absolutely the same expressions, but without symbol R. From here, okay, and let us compute the change of total entropy in this quasi-statical process. Okay. ds total equals ds plus dsr. Here I have 1 over tr, okay, 1 over t du plus 1 over t r dur sub r plus d over t dv plus pr divided by d sub r dvr. Okay, but this is not all. We know that the total volume and total energy of our system, big system, closed system, do not change. This means that we have a consequence here. Okay, 1 second. I want to write in blue whiteboard marker dvr equals to dv and dur equals minus dv minus du. Okay. And we can continue. I get 1 over t minus 1 over tr du plus 1 plus p over t minus pr over tr dv. Okay, this is the change of total entropy. But on the other hand, we know that the total entropy has extremum in the equilibrium state. This means that its differential should be 0. Now we can consider, we can go further. If our system changes with environment by energy, we have a condition 1 over t. This means if it can change by energy, this means that differential of u is non-zero. And it is the same that temperatures are equal. This conclusion can be formulated as follows. If the system is in equilibrium with environment and it exchanges by energy, that means a thermal contact this means that the temperature of our system and temperature of environment are equal. This condition is very important for us because it tells that in fact the temperature is a quantity that is equal for all the systems that are in thermal contact, maybe that are in equilibrium in thermodynamics. We told previously in one of the first lectures that transitivity of equilibrium, of thermodynamic equilibrium, implies that there is a quantity that is equal for all the systems that are in equilibrium. Now we see that the temperature T is this quantity. Okay. The system can change volume if we have a mechanical contact. Mechanical contact means that system can make work over environment. This may have place, this constant contact may have place or may not have place. So this is not necessary condition. This is necessary. This condition is always satisfied because all the systems that are in contact, they exchange by energy. And here we have another conditions. We see du and dv are independent quantities. So we get P over T minus PR over TR equals 0. But if the temperatures are equal, we conclude that the pressures in the system and in environment are equal. This condition has a very simple explanation. Suggest that we have some, let's say, reservoir, let's say it is gas, and we have some body, maybe let's say piston, a body that can be changed, can be moved from here to here. And we have here we have gas 1, and here we have gas 2. And if this body it has non-zero thermal conductivity, so they can exchange by heat, gases. So, and it can move. So our conditions say that in equilibrium state P is equal in gases and T it is equal in these gases. It's quite natural because if pressure is equal, the force that acts on this body from the left and from the right are equal. And this the equality of temperatures means that they have one and the same temperature. If we fix the body, the volume is constant, and we have only one condition that concerns temperatures. It's very important. So this we have if we have thermal contact, and this if we have thermal and mechanical contact. Thermal and mechanical. Okay. So we see how to determine the state of a system that is open. Okay, if we find is that the pressure and temperature are equal from the left and from the in the system and environment, okay, we have an equilibrium state. What is the? So we finished only half of this question. What is the problem? Okay. What is the problem? In fact, there are very many thermodynamical systems which can be more complicated than this one, and they may have higher number of thermodynamics degrees of freedom. This may happen in the systems that have complicated structure. Let's say they have many pistons and so on, many gas reservoirs and etc. And this can happen in systems with in which amount of substance change. So there may be some other parameters. And we should add parameters to environment. And in this case, if we have a bigger number of parameters, we should formulate another principle. Okay, one principle that we can, if we add something here, some parameters here and here, we could repeat our calculations and obtain some conditions. This is not convenient by one very simple reason. When we have a closed system, we have only one function whose maximum determines an equilibrium state. And here, when we have a complicated system, we would like to formulate equilibrium condition as an extremum. It could be maximum, minimum, we will say later, for one single function. We want to say the system is in equilibrium with environment if some function is maximal or minimum. And now we are going to formulate this. Condition. The task is not simple, so we choose the model of environment. We should choose the model of environment. I mean that we should describe environment as a thermodynamic system. Okay, in all the real applications, environment is a very big system, which is much bigger than our subsystem of interest. This means that environment can be considered as a reservoir. Let's say reservoir of work, reservoir of heat. What I mean when I say heat reservoir? I mean that environment has a constant temperature Tr. Okay, not constant, but to say another way. The system has very big heat capacity, and its temperature in all the processes that happen in the process of interaction with our system do not change. And the temperature of environment is Tr. And it could be reservoir of work. Reservoir of work, it means that it has a constant pressure. And if the volume of our system changes, the pressure of our system of environment do not change. So, okay. And now we choose the model of environment, and we are going to find an equilibrium state. Let me recall that our system is complicated. It has many many degrees of freedom. But I do not write out the corresponding variables because they are not interested for me. And here let me write some maybe paragraph. And our first task is equilibrium. in contact with heat reservoir. This is a situation in which our system can exchange with environment by energy, but its volume and all the other characteristics of the system do not change. Only thermal contact with environment. You can write in your copybooks that we have a thermal contact. And there could be process of exchange of heat between the system and environment. And let us suppose that some portion of heat came from our environment to our system. Okay. Okay. It's so okay. Let us suppose. Then, if such portion of heat came from environment to our system, we can write out dUr minus delta Q. It's the first law of thermodynamics applied to the environment. And we can represent this quantity in the form minus Tr dsr. On the other hand, from here, dsr equals minus dUr. Okay, let me du minus t minus, okay, dUr divided by Tr. And because the total energy of the system is constant, I can say that this is du no, it's not correct. The sign here is not correct. So here plus and here minus. du divided by Tr. Okay, this condition connects the change of entropy of the environment and the change of internal energy of our system. Let us now compute the differential of total entropy. I have here ds plus dsr okay. Here I have ds, it's not a problem. Minus du divided by Tr. And here I write this in this way, minus 1 over Tr d u minus Tr s. And this is a free energy, F, free energy. So, have here. This condition means that the free energy of the system reaches in extremum, let's say, reaches extremum in the equilibrium state of the system, of the open system that has thermal contact with environment. Let us determine the type of extremum. We know that entropy tends to maximum. This means that in all the processes in the closed system, the differential of entropy is positive. From here, we conclude that dF is negative or zero. This means that the type of extremum is minimum. Let's say minimum. F tends to minimum. There is a very simple rule that describes the state of such system. I should attract to your attention to one point here. Look, here not free energy general, but free energy for temperature. When the temperature equals to the temperature of heat reservoir. This means, and let me formulate the rule. That means that for here the formulation, in the equilibrium state of open system that is in contact with heat reservoir, the free energy of the system reaches minimum for temperature reaches minimum and for temperature which is equal to the temperature of heat reservoir. So, to find the equilibrium state, we should make two steps. First, we should construct a function. Let me denote this function Fr equals free energy, where we took temperature equal to the temperature of reservoir. And that this function should be tend to minimum. Okay, I suggest to make a 5 minutes break. You may ask questions if you want. So, let's consider another question. Suppose that we have a more general type of contact between the environment of our system, and say that they can exchange by one additional characteristic, which I again call volume. This may be not indeed a volume, but maybe some other quantity, but it should be a macroscopic parameter of our system. I just say volume to be concrete, and suggest that the system can exchange with this additional quantity with environment. Okay. And now we are going to find the state of the system in this type of contact. So the question is position 2 with heat reservoir and work reservoir, to reservoir of work. And this corresponds to thermal contact between the system and environment and mechanical contact between the system and environment. Okay, so let us again apply the first law of thermodynamics to the environment. And let us compute the differential of entropy. Not differential, that's differential of internal energy of entropy. It equals to TR DSR minus PR dVR. From here, we express the differential DSR as follows: 1 over TR DUR plus PR over TR dVR. Okay, next we will use this relation. But let me attract your attention to another important point. Here the TR, PR and are constants. This means that this equation can be integrated. And from here we see a fundamental equation of state, fundamental relation for the reservoir, and it's a linear function in UR and VR. Okay, let me attract your attention to this point and let us continue. As usual, we compute the differential of total entropy of the system. This quantity should be non-negative. In all the processes that come in closed system, so we have ds plus dsr. And from here, I can ur and vr replaced by minus u, du and minus dur. du minus du and dv. Okay, and here I have ds minus 1 over dr du minus vr divided over dr dvr, and we replace this condition as follows: 1 over minus dr differential of u minus drs plus prv. And this is the free energy of Gibbs. So this means that the free energy of Gibbs reaches extremum in the equilibrium state of such system. The type of extremum is minimum, because here minus and here entropy takes maximum. From here we have a simple rule for determination of equilibrium state of the system that has mechanical and thermal contact with the environment. And let me say the formulation. In the equilibrium state of the system, in contact with heat reservoir, and work reservoir. The Gibbs free energy, maybe another term is Gibbs potential, takes minimum value for temperature equal to the temperature of heat reservoir and pressure being equal to the pressure of work reservoir. Why this conclusion is very important? Let me take this one bottle. And in this bottle, inside the bottle, we have a thermodynamic system. It includes liquid and maybe some vapor. And we can ask ourselves, what is the equilibrium state of this thermodynamic system that includes liquid and vapor? And our computations give a simple recipe for finding of equilibrium state. It's the state with the minimal possible free energy of Gibbs with additional restriction. We take temperature equal to the temperature of heat reservoir, this means the atmosphere in this room, and pressure being equal to the pressure of work reservoir. And here, pressure of work reservoir is atmosphere. So, this is very simple recipe for computation of equilibrium state of such system. And this rule can be generalized for absolutely general type of contact. Let me formulate general rule, which I explain briefly. And so let me suggest that I have a system, okay, that have certain parameters. Let me denote them x1, okay. Let me say xm and something else. And the system can exchange with environment by heat. So it means that we have a thermal contact. It can exchange by environment with these parameters. I mean that the x1, let's say, and so on, the xm, say, are non-zero in general. There may be some other parameters that are constant in such type of interactions, and they are not interesting for me. And we have okay. So, and for environment, we should choose the following parameters: UR, SR, and let me denote X1R, XMR, and let's say something which are not interesting for us. And these quantities should have conjugated parameters x1r, xmr. What what I mean conjugated parameters? I mean that du r equals dr dsr plus sum over I to m x1 r dxir dxir. So in the previous example we have only one x and it was equal to minus b. Okay. And in this case we find the following condition. Then differential of u minus dr sr minus sum u from 1 to m x1 r x1 not xir, okay, xir greater than 0. Let me skip the details of computation. Okay, and let me denote all the inside by some Greek letter phi, big phi. It's by construction, it's a thermodynamic potential. By construction, phi is a thermodynamic potential with natural variables T, xr, x1r, xmr, and if we had some other extensive variable here, z here. And this quantity, okay, no, this is incorrect sign. Mine should be less than. And this quantity and this rule says us that if we have an open system that is in contact environment, which is a reservoir of temperature of and certain extensive parameter x small, in the equilibrium state, the thermodynamic potential that includes that has natural variables, that has the intensive quantities as that has intensive quantities as its natural variables, and if it has some other quantities, they remain here. This potential should be minimum in the equilibrium state. And the minimum should be computed for the parameters in the case when the parameters, extensive parameters of the potential equal to the extensive parameters of reservoir. This is a very general rule. You can try to rederive it and so on. Okay. We have finished with the first question, and let us discuss the issue of stability. And let us return to the simplest picture which had in the very beginning. We assume that we have volume as a characteristic and maybe some other parameters, but they do not change. and we have interaction, between of our system and environment. Let us suppose that we have both thermal and mechanical contact. This means that both the energy and both the volume are changed. Volume are changed. Okay. And okay, we can see this question we consider this question, and now we see, and let me give one very important point. As far as we all know, exchange between energy, by exchange of energy and volume between system and environment, these changes inevitably happen. This means that the volume of open system always change by little quantities. It's very simple to explain this fact using microscopic picture. Say we have some reservoir with gas, but the walls of reservoir are not rigid. They can change the shape. And if the molecules of gas inside and outside of reservoir bite by the wall, its shape changes and the volume changes. The same for the energy, because in collisions it will be change of energy between the gas particles and the walls between the gas particles inside and walls and gas particles outside and walls. So we certainly have some exchange of energy. And these small changes are uncontrollable. We can't control these changes if the system is open. So from time to time, the volume of the system will increase or decrease, and the energy of the system will decrease or decrease. And we should be, and when we say that this system is stable, we mean that all these changes are only for short time. After some time, the system will return for sure to the initial state, which is said that the state of equilibrium. And this return to initial state will happen, and this is the concept of stability. There are fluctuations, but system will return to the initial state. This is stability. But to ensure that the system is stable, we must say that the entropy in the state, in the fluctuation, is higher than the entropy of the system, is higher than the entropy of the system in the state, let's say, in the state of equilibrium. To find a necessary conditions of stability, I suggest that we have a little fluctuations. That means that the volume of the system changed and the energy of the system changed. U goes to U. And I'm going to compute the total entropy after fluctuation. Total entropy after fluctuation. I mean, I choose U equals u plus du, v plus dv. And let me stress again that we have that the environment is special. It's a reservoir of heat and reservoir of work. Means that the parameters of reservoir are constants. Okay. I'm going to compute the entropy in the state of fluctuation. And let me compute. Okay. Let me say that its initial entropy, certain initial, plus. Okay. Let me compute in the other way. It's not a good idea. Okay, by construction we have that the total entropy is equal to the entropy of the system and entropy of reservoir. And now I compute the entropy in fluctuation. So I decompose. Okay. So I decompose this one in fluctuation. Up to second order in volume and internal energy. Okay. So let me write S0 plus S0 there. This is the value of entropy in equilibrium state plus ds by du by dur plus ds by dvr plus not good idea. Okay, not good idea. Again, not good idea. Let me write out in this way. S plus SR in the equilibrium state plus differential. Okay, maybe it's better here. S total 0 plus ds total and plus, let me write out this way, d double s total. This means that it's a second order correction. Okay, this is some constant, and in the state of fluctuation, the difference S minus S0 should be positive. Should be negative. Should be negative. Let me explain. I will explain why. And here, this equals ds total plus d second s total plus and here. So, what is this? It's a change of entropy on fluctuation. If we want stability, the entropy in the state of fluctuation should decrease. So this difference should be negative. When the entropy in state of fluctuation is lower than entropy in equilibrium state, the system will return to the state of equilibrium after some time. So this condition ensures stability. And now we decompose this difference in the parameters du and dv, which means the size, it characterizes the size of fluctuation. I decompose this difference up to the second order. The first order is 0, because this is the condition of equilibrium. The condition is equilibrium by one reason, by one simple reason. We know that in equilibrium state, the entropy, the total system, reaches maximum. And maximum, the differential of the function is 0. And the first order correction contains non-trivial information. And we see that this differential should be negative. Now, okay. Now we can proceed. Let me recall that total entropy is the sum of entropy of reservoir and system. So, by linearity, we can write out is this way. And here, very important point is that this guy is 0. Because SR is linear in UR and VR. This fact we have shown a little bit earlier. That's why I see that S total in state of fluctuation minus S in equilibrium state equals to d second S plus, and this is non-negative. This condition means, in fact, means that the differential of entropy function of system should be negative everywhere, because I can choose parameters of reservoirs as I want. I conclude that for T equals TR, P equals PR, this is the parameters of equilibrium state, but these parameters are arbitrary, so due to this second derivative of S is always negative. This characterizes the entropy function of the system. If I make a plot of the entropy in the coordinates u and v, I will see that the entropy has some kind of cup form. This should be. And this is a geometrical meaning of stability conditions. This is geometrical meaning. And we are going to find the physical meaning of stability conditions of the system. Let us compute the second derivative of entropy of the system explicitly. this is 1/2 d second s over du, second derivative du squared, plus the second derivative, okay, du dv, plus 1/2 the second derivative of s by dv quadrat, dv second power, dv second power. And this quantity should be negative. In the right hand side, we have a quadratic form in arguments du and dv. This quantity, the second derivative of differential of s, is non-positive if this quadratic form is negatively defined. Negatively defined. This means that it's negative if 0, here you can write same. This means that it is 0 or negative for arbitrary values of du and dv. You can derive very many these conditions. These conditions are in many ways. I will apply Sylvester criteria, and it says that we have two conditions here. Second derivative of u is less for v constant, and here for u constant. For v constant is negative, and this square this condition says that for when we say dv 0, that we have only fluctuations of u. In this case, entropy must decrease. This condition says that when we have both the fluctuations of energy and volume, we should have a negative fluctuation. And alternative condition is to consider at first fluctuations of volume and then combined fluctuations of volume and internal energy. So we get here. These conditions are equivalent because these two guys imply this one, and this pair always implies this one. Let me suggest for you to study this fact, to see this fact yourself. And we are going to study physics. So, what these conditions mean? And I will consider these two guys in more details, and these guys less detailed. So what is the second derivative of entropy? Okay, I represent second derivative as a consecutive derivative. So I get here this way, and ds, and from here, this derivative we find from the thermodynamic identity. It's a temperature. So I have derivative dt over du for constant v, and this is t, and this is 1. Okay, I'm not correct here. From this derivative is 1 over t. So I have minus 1 over t squared dt by du for constant v. And here I get 1 over t squared, and here I get the heat capacity. And this quantity should be negative. As far as temperature, the square of temperature is positive. I get first condition. Cv is greater than 0. This means that heat capacity of stable system not greater than 0, that the heat capacity of stable system must be a positive quantity. This is quite logical. This means that when the temperature gets some amount of heat, gets some amount of energy in the form of heat, its temperature increases. It's quite good. If this condition is violated, so if we would have here sign here, this would imply that the temperature of the system decreases when it gets energy. So it will get more and more energy, and its temperature will decrease. This is unrealistic. The condition of stability is this one. The second condition is quite complicated, so I need some consultations here. So let us rewrite the second condition. Squared minus d second s over dv squared u d second s over du squared over v. Okay. And I make very interesting thing. I will represent this derivative. I represent this derivative in two different ways. So I can du by dv, ds by du here, and here I will get d by dv over 1t for constant u. And here, and I can act in another way. I will get d over du, ds over dv, and here I will get here p over t with constant v. And after simplifications, I will get from here, let me write out this one. Okay, I write out the result because I want to skip all the computations, and here we have bracket, big bracket, dt over dv for constant u, dp over du for constant v minus dp dt over dv for constant u, dp over du for constant v. Here you see that here we get derivatives, and then maybe make a simplifications and get this one. And this is in fact a determinant. T squared, p squared. Okay. What is the question? Okay. D T P D U S. And I'm going to simplify this determinant. I keep minus D TP D VS D VS. I insert VS here and here. These do not change nothing. And this will give me a P, 1 over P, with a minus sign. So this guy is minus 1 over P, dTP, dVS, and then I make another simplification, dTP, dVT. I need maybe, let's say, maybe 5 minutes over lecture. Please let me finish my lecture. VT, D, VS. And here I get T over P. And from here, this is T over heat capacity, CV, T over P, dP by dV for constant T, over CV. And this quantity should be negative. This means that from here I get the condition dP over this guy is positive, this guy is positive, maybe okay, positive. So I get the condition dP over dV divided by T. Think here du by dV. Okay, let me check the signs. Maybe okay. For constant T is less than 0. This condition, the quantity is isothermic compressibility. Maybe this quantity, the quantity of isothermic compressibility is the following: 1 over V dV divided by dP. Okay, this is, let me say, this as far as I remember this is letter beta. Okay, and this quantity should be negative. This condition instability has very simple meaning. It says that the increase of the pressure will lead to decrease of volume, and vice versa. If the volume is increased, the pressure is decreased. This means that the gas resists to its compression, and again it resists to its extension. And it's quite natural, so we have another stability condition. The other pair of condition involves the second derivative, this one, and should be negative. Let me not to write out this condition. Let me say that it leads to this one. It's adiabatic compressibility. Summarizing all the above, we see that we have two alternative of conditions of stability. In the first case, we say that heat capacity is positive, and here should be strict sign. And adiabatic compressibility, not adiabatic, isothermic compressibility is negative, and it's the same to say that adiabatic compressibility here P and isothermic compressibility is non-negative and adiabatic compressibility is negative. Okay, and this is a resume of the second condition. These are stability conditions if we allow fluctuations of volume and internal energy. If we allow fluctuations of other parameters, maybe we have a more complicated system, we will have more conditions. I do not write out them because they are complicated and you can derive them yourself. So the lecture is finished. If you have questions, you may ask them.